have dinner.
Okay, so now we're ready for Mirjam Cvetic, and you can read the title yourselves.
Well, I would also like to thank the organizer for kindly inviting me to this conference and to present some of the recent work I've been pursuing. It's actually a great pleasure to be here in Madrid after a number of years being absent. And it's also a great pleasure to enjoy the new institute here and the new building where the conference is taking place. So the topic of my lecture is to, just a second. Is to address certain global constraints in F-theory, in particular those that are associated with the gauge symmetry and the constraints on matter representation. The actual focus in studying those global constraints will be for implications that arise in the presence of Mordell-Weil group on elliptically fiber Calabi-Yau manifolds. Well, in the first part, we are going to look at the free part of the Mordell-Weil group that is associated with U1 gauge symmetry in F-theory, and we'll emphasize some new insights into global constraints on gauge symmetries and representations where we have, in addition to U1 gauge group, also non-Abelian gauge symmetries. And in particular, I'm going to highlight some implications of these global constraints also for F-theory swampland. In the second part, we'll focus on the torsion part of the Mordell-Weil group, which is associated with modding out non-Abelian gauge factor by a discrete symmetry. And here what I'm going to highlight is novel non-Abelian enhancements of gauge symmetries and a new type of matter that arises in such processes where we are dealing with the torsion. And I'm going to also, at the end, mention a few open issues in this program. The first part is based on a work with Ling Lin, and it appeared last summer. And the second part associated with the Mordell-Weil torsion is together with Florent Baum, Craig Lowry, and Ling Lin. So the nature of U1 symmetries in F-theory is somewhat different from those associated with the appearance of non-Abelian gauge symmetries. Namely, the 1-1 form supporting U1 gauge bosons should be associated with I1 fiber, since we need those forms to be isolated. So the 1,1 forms are in 1-to-1 correspondence with rational sections of elliptic fibrations. Or when we go just down to elliptic curves, it's associated with the existence of rational points on elliptic curves. In Weierstrass parametrization, in addition to 0 point, if we specialize the representation of Weierstrass formula in such a particular way that we encounter additional rational points, those points form a group under addition, with the 0 point having a role of the identity. And the type of group that is this type of group under addition associated with these rational points is referred to as Mordell-Weil group. So these rational points actually induce in the vibration rational sections, and these rational sections give technically rise to a second copy of a base in this elliptically fiber Calabi-Yau manifolds, and thus create a new type of divisor. Employing this particular divisor via Poincare duality, we consequently can thus uniquely construct the 1,1 form that indeed supports the abelian gate symmetry in the construction. So let's focus first on implications of free part of this Mordell-Weil group associated with the rational sections. The actual construction of the correct divisor that would support a U1 gate symmetry is not just a simple it's not just a simple copy of the base divisor BQ, but is actually constructed via so-called Shioda map, where this Q divisor actually in the Shioda map has to be mapped in a complementary way to the zero section divisor, and also a specific linear combination of resolution Cartan divisor of non-abelian gate symmetry. So this Shioda divisor is really the proper divisor that we have to construct to have the proper F-theory interpretation of U1 gate symmetry, and it's also properly identified and checked via M-theory, F-theory duality. So in this construction, we see that the linear combination of resolution divisors associated with cartons of non-abelian gate symmetry has coefficients which are actually fractional numbers, and this comes is a consequence of the fact that these fractional numbers appear in terms of inverse Cartan metrics, and the intersection of the Q and zero section divisors with the fiber of specific divisor, resolution divisor. So these fractional numbers always allow us to find an integer for which multiplication of these fractional numbers with these integers is then always integer number. So this kappa will play an important role in the subsequent discussion of the properties of the charges of matter representations in this construction. So in particular, U1 charges of matter representations are obtained through intersection of Shioda divisor with the corresponding matter curve in the fiber, and so all matter charges from this construction are necessarily multiples, integral multiples of this 1 over kappa, just as it arises from the intersection numbers associated with this calculation. So, in the presence of non-abelian gate symmetry, we have representations that transform non-trivially under this non-abelian gate symmetry, and from there, from the properties of this Shioda divisor, we can identify that two weights associated with the same non-abelian representation actually have the property that the products of these coefficients Li with the weight coefficients are for the same representations the same modulus Z. So this fractional number modulus Z basically quantifies the key feature of non-abelian representations. Yes? Oh. Did I? So in particular, if we want to identify now the specific U1 charge of such non-abelian gauge representation, we can deduce from these intersections that actually the U1 charge is basically related to these fractional numbers. So they are integral multiples, basically, of the same, of the value of this product of Li weights with Wi weights with the coefficients Li. So what we want to now identify is the actually the specific non-trivial central element of a product of the U1 cross non-abelian gauge symmetry by employing that U1 charge are integral multiples in 1 over kappa, the properties of the actual weights of the non-abelian representations. And as a consequence, one obtains that when a central element that acts on particular weight is indeed central by this construction, and furthermore, its power, kappa's power, it becomes identity. So with explicit construction of a central element, we have identified that, there is the symmetry, discrete symmetry of order n that now modifies or quantifies further the global gauge symmetry that has to be modified out by this central element. So basically, the Shioda map in the presence, namely in the presence of U1, the Shioda map produced for us global constraints on non-abelian gauge symmetry. So in the presence of non-abelian gauge symmetry and an abelian factor, in principle, there is a central element by which we have to mod out to the global structure of the gauge symmetry. So one can exemplify this for the case of SU5 GATT models and as well examples of different standard type model constructions. But let me just highlight the example of globally consistent three-family standard model that is based on a toric construction with fluxes and produces the gauge algebra of SU3 cross SU2 cross U1, and it has 3 copies of quarks and leptons. The Shioda divisor associated with the U1 is now a combination of the Q and 0 divisor and specific combination of the Cartan divisors, from which we can now concretely deduce that the central element is of order 1, and as the global structure of this model is the standard model symmetry group modded out by Z6. So indeed, the explicit construction of chiral matter representations in this model produce the non-abelian chiral matter that has precisely charges that are compatible with the order 6 discrete center. No, for its own sake, it's direct construction by identifying generically SU3, SU2 divisors. We did not look at the deformations themselves enough to see whether we could undo that or unhix possibly these things. Keep in mind it also involves Mordell-Weil. And so, in any case, but this was just a brute force construction. In retrospect, these general arguments that I was spelling out are indeed formed in this case, right? And the matter really follows this. So, actually, these global symmetry constraints have implications for the swampland criterion, criterion which we formulated with a certain assumption that there exists in the construction a matter singlet under non-abelian gauge symmetry that has the U1 charge that we can associate it with as a minimum charge 1. This basically defines the scaling, the freedom in the scaling, in the overall scaling in the Shioda map. Okay? And we would use the singlets as measure sticks to determine our charge quantization. Okay? And then as a consequence of global constraints, a necessary condition for a field theory to be now in F theory requires that this U1 charge constraints have a specific conditions on non-abelian matter. Namely, one can deduce from just all these constraints that if we have now in the presence of this measure stick singlets, non-abelian representation, say that we have two copies of matter with the same non-abelian representation, but different U1 charges, the difference of those U1 charges has to be a multiple of an integer. Okay? So there could be anomaly-free field theories that have examples where this is not the case, but they would not fall into F-theory construction per se. Okay? And there's another refinement also that the tensor product of different representations that contains a singlet would always have to involve U1 charges of these representations whose sum is multiple of integers as well. So if you have a field theory that violates those properties, then this is not a field theory that is constructed from F theory. Okay? The caveat would be the existence of non-Higgsable U1s, namely the fact that we don't have a measure stick, say, of a matter singlet. But in the presence of non-abelian matter, one really expects that in addition, if you already have non-abelian matter, you would also have singlet representations, and thus they would act as measure stakes as well. So with just these assumptions, I think we are quite safe about covering the full F space. Okay? Just another minor comment. One could further study now the unhixing of this U1 in the presence of non-abelian gauge symmetry. And interesting enough, we encountered different models. In particular, some of the models involved in the unhixing, the non-minimal codimension two loci, namely matter representation that does not fit into Kodara classification, and so is related to strongly coupled CFTs, and that's definitely a topic that deserves further study. Okay. One issue that one can ask oneself, I use completely geometrical arguments to determine constraints on matter representation and the global symmetry structure. How about if we had fluxes in this construction and some of the massive some of the U1s become massive, which is typical, the example when we go down to 4 dimensions. So in the presence of multiple U1s, we expect to have, again, our measure sticks, namely singlet fields with co-prime U1 charges that are measured with the Shioda map associated with U1 generator. So each U1, as a consequence, would be associated further with charge constraints on non-abelian matter along the same lines I presented for the of U1 cross non-abelian factor. Now, when we add fluxes, we would these fluxes would break specific combinations of U1s via Stuckelberg mechanism and make them massive. So the mass matrix is a bilinear combination of Fayet-Leopoluz vectors that are determined by the presence of quantized G4 fluxes. Now, massless linear combinations could still be there. Namely, they would be combinations of original Shioda divisors that sit basically in the kernel of this mass matrix. Now, one key point that we see here is that the Fayet-Leopoluz vectors are actually integers due to the quantization of G4 flux. And as a consequence, the linear combination of U1s that sits in the kernel of the mass matrix can also be written in terms of integer numbers. And as a consequence, then the massless linear combinations again its generators again span a sublattice of Mordell-Weil group, and the geometric properties leading to the charge constraints that I derived prior to that still holds in this context. And basically, we see that happening in those examples. So the whole story can go all the way down to 4 dimensions. Okay. So in my second part, I would like to turn now to the issues related to the torsion, Mordell-Weil torsion, and how it's related to the nature of gauge enhancements in F-theory. So the part that I was focusing up to now was the existence of a free part of Mordell-Weil group associated with the rational sections, and now I'm going to focus on, also on the role of torsional sections. So if we attempt to do a Shioda map for torsional section, the Shioda divisor basically has to satisfy constraint that it adds up to 0. As a consequence, the integer condition on charges tells us that this linear combination of Li with the corresponding weights has to be an integer, and a consequence of this this constraint is now that the nature of the gauge group that we have in the presence of torsion is that the global gauge symmetry is modded out by the Zn factor, Znk factor, where Nk is basically the common integer by which this fractional 1 over this integer that basically determines the integer values of Li. Yes. So, so what we want to ask ourselves in this context is what type of gauge enhancements we encounter when we start with a section, namely with a free part of Mordell-Weil group, and deform it in such a way that it becomes torsional. So as I was already indicating is that tuning a free section to sit on top of a torsional one, say of order n, we would expect the enhancement of gauge symmetry from U1 generically now to the one that is associated with non-abelian symmetry modded out by global factor Zn. But in what manner does this happen, really? So again, we expect that this U1 to unhix to non-abelian gauge symmetry whose first homotopy group is Zn. Okay. Now this unhixing seems to have strong parallels with the unhixing when we are colliding just free sections. For example, that was studied in the work with Evers, Piragua, and Taylor, and we looked at the collision of two U1s and in the presence of matter that was generically charged 2,2 under 2 U1s. Such an unhixing process, both geometrically and field theory, produces SU2 gauge symmetry, where there is, out of this matter charges, where one actually ends up in the unhixed phase with the non-abelian gauge symmetry and the symmetric representation of SU3. And that was actually the first example of explicit F-theory construction of symmetric representations. So these ideas can be generalized by looking at the models with, say, single U1 and charge 3 matter that would unhix to SU2, and there the charge 3 matter unhixes into 3-index symmetric, 3-index representation of SU2. So how does this analogous unhixing happen in the case of torsional unhixing? And for the sake of specificity, let me choose a prototype to be unhixing to Z2 torsion. Okay? So the first example that was addressed in the work by Meyerhofer, Morrison, Till, and Weigand looked at the example of U1 with charge 1 matter that is unhixed to SU2 mod Z2, namely SO3, and now this charge matter turns into triplet, a joint representation of SO3. Basically, this matter charge unhixes into something that effectively in the unhixed phase has cartesian charge too. Now, what we want to focus on is how about charge matter 2 in the presence of torsional unhixing of U1. What is the full-fledged unhixed gauge? Is it SU2 cross Z2? What is the matter representation? Well, one would hope that charge 2 matter would unhix to much higher representation, and by this analogy, okay, one would expect that one has a chance here to get really higher index representations with this torsional unhixing. But I have to give you a spoiler alert. The expected cartan charge 4 unhixed representation, which would be 4 index representation of SU2, really doesn't turn out to come through this unhixing process. And this sort of indicates that there may be, these constraints on possible representations that we typically encounter in these processes may also indicate to limitations of representations in F3 compactations, and is possibly to other swamp-like conjectures, such as those we heard in Watty's talk and possibly in Roberto's talk. Okay, so I have just a little time to highlight the properties of gauge enhancements via this Mordell-Weil torsion in the presence of charge 2 matter, and we are going to use the Morrison-Park model with U1, and unhix the additional section to Z2 section, to Z2 torsion, where, of course, the Mordell-Weil group is expected to gain a Z2 torsion. The outcome of this analysis is that the gauge symmetry is much larger than expected. Namely, it's of the structure of SU2 cross SU4 mod Z2 cross S2, and it has new features. Explicit global models, it shows us first example where there is a non-abelian factor that is not affected by torsion, and there is a new type of matter associated with codimension 2 fiber, which is a new matter of 3,2, and unfortunately not 5,1,1. Okay. Let me just, if you give me 1 minute, let me just point out that there we also address another example, which is a Higgs version of the previous one, where actually we construct a fibration that has that type of gauge symmetry, which is sort of interesting, is SU2 modded out by torsion, and it has also discrete symmetry Z2. Z2 symmetry typically signifies a bisection, and it's associated with Tate-Shafarevich group. And indeed, this construction involves directly genus 1 fibration that does have a bisection. However, the gauge symmetry part, non-abelian gauge symmetry part, we actually identify in the Jacobian map, which had a resolvable I2 singularity in codimension 1, and Z2 Mordell-Weil torsion, thus signifying SO3 gauge symmetry. But in this model, there are still puzzles that we are dealing with. Namely, one is the genus 1 fibration with bisection has a monodromy that exchanges components of I2 fiber in codimension 1, and thus we are missing in the bisection construction exceptional divisor that would signify non-abelian gauge symmetry. And this also is puzzling because in M3 that would be pointing out to missing divisor of non-abelian gauge symmetry. Another puzzle we have that in the Higgsing chain analysis, we expect existence of discretely charged or joint representation of SO3, which should be localized in codimension 2, but we don't seem to see that neither in the bisection nor Jacobian construction. So that really us to the need to sharpen and augment the definition of F theory on genus 1 fibrations and their Jacobians. So I sort of highlighted few novel implications for global properties of F theory in the presence of Mordell-Weil group. we encounter subtle issues, first with the free part, namely the presence of U1. When we have non-abelian gauge symmetries, constrains full global structure of this non-abelian gauge symmetry, and also matter charges, and thus leads to specific swampland conjecture in this context. Torsion part gave us new type of gauge symmetry enhancements and new representations, but what we encounter is much more obscure, difficult issues that point to better understanding of IFT reconstructions on torus vibrations without sections, which is clearly a topic of future studies. Thank you.
So, purely from field theory, the question of the global structure of the gauge group is a question of extended operators. For example, you're looking at one-form symmetries, so you're looking to two surface operators in 4 dimensions. Can you see those in the theory construction?
I have to say I have to draw those lines. I don't have the answer to that specifically. This is purely geometric arguments from Shioda mapping constraints we get about possible U1 charges. So, but it's worth, we can discuss that privately. Thank you. Indeed, the y of the section was set to 0. That was the picture that I was basically using. Just you can basically, yes, exactly. The y of a section is 0, and then that's what this picture signifies. Actually.
Good, thanks.
And it is E2 torsion, yeah.
Maybe you mentioned it, and maybe it's related to also the question Jonathan asked, Wari, I'm not sure. So the U1 with charge 1 was a question that Jonathan asked, whether you always have charge 1 as your master states. And you also have this issue about U1 with the minimal charge 1. I do not know if they are related issues or not, but the question to you, Wati, or maybe to Mirjam, is whether or not in your infinite family you had cases where you did include have charge 1 or not. And as if you insist on charge 1, do you also still have infinite family? Absolutely. That doesn't cut it for you. Not the relatively prime I'm talking about master's charge 1. That doesn't change it either. And for you, what was the issue about the charge 1?
This is how you basically normalize your charge properly.
Sorry, there is an absolute normalization if you insist on integer charges.
So another option is, I wasn't as precise, that this is a natural choice to have just Q1 massless charge. State, right? You can have also, if you have massless singlets with co-prime charges, that also suffices to define your normalization. That would be the other option, right. Okay? And basically, I don't think you have any counterexample yet.
What's that?
From FT construction.
Well, we know there are only a finite number of
yes,
theories, so we have an infinite number of counterexamples. We just don't know which ones they are.
Right.
That's right. So we don't have any specific model that's a counterexample, but we do have an infinite list of counterexamples.
Right. Of course, just to make a side point, you could, if you have, you can easily construct field theories in 6 or 4 dimensions that would violate for non-abelian matter this integer condition. Okay, very easily, they are anomaly free, even gravitation, everything works, okay, and yet they are not coming from F theory per se. Okay, so what I'm trying to say, if you have non-abelian matter where the U1 charges are a difference of them is non-integer, they could be perfectly anomaly free by all field theory constraints, and yet they don't fit into this picture.
I think we're saying the same thing, that once you include U1s, it's much harder to constrain the models.
Yes. Okay, but F theory has very little room, really, in this. This is sort of the message here.